at your packet, this is where we left off in class. So just using this formula to calculate the amounts for different compounding periods. So notice there's not a huge difference. So it appears the more frequently you compound, you make a little bit more money. So this kind of leads us to this next idea, which is called continuous compounding. So as n gets larger, we saw that there wasn't really a difference. If you look at the last two for the hourly and the every minute, there really wasn't even any difference. So, so this idea of compounding continuously in this formula actually comes from calculus. So this is a formula we can use. Remember, E is a number, approximately 2.718, 28, 1828, etc. It's not a repeating pattern. The numbers are different. I think it's 45, 90, 45. You do have an E button on your calculator. There's two of them. You can find them one, well, let's see, I'll show you. So you've got one above the LN key. So if you go second, LN, you can access that, which you guys already know. And then the other one is above the divide by, so you can see that. So what we have on this one is this other formula. So using this, P naught is still the initial, the principal. R is the rate you have to write it as a decimal, the annual interest rate. And then T is time in years. So for this first question, how much is $5,000 invested at 4% APR compounded continuously worth? So we would end up with P equals, P naught is 5,000. And then we have E to the RT. And they didn't have a particular time, but let's say 10 years because that's what we did in the previous chart. So if we evaluate this, notice that we get about $7,459.12. So if you compare that, $7,459.12, you see we get the same, rounded to the hundredths place, we get the same answer. And this is just a very easy formula to use if this idea of compounding continuously. So this next question says $100,000 is invested for 20 years at 3.5% interest APR, so that's annual percentage rate. How much more money will be gained by continuous compounding over daily compounding? So we're basically being asked to do two different questions here. One of them is using this formula. So when we calculate that, we're going to take 100,000 times E to the 0.035 times 20. So that's going to be one of the values we have to calculate. And then the compounding daily, we're using P equals P naught. And for this one, if you go back to your formula, so we're going to have 1 plus R over N to the NT. So we get 100,000. 1 plus, the rate is 0.035. If we're compounding daily, then N is 365. And we would have 20 times 365. So for this first one, we get $201,375.27. And for this second one, we get $201,368.51. And the question is, how much more money do you get by compounding continuously? So if you subtract those, then you would find that you get $6.76 more. So obviously, not a big deal, not a significant amount. So this next question says, suppose you invested $1 in a bank at 5% interest and simply left it there to gain interest. If it's compounded interest according to the continuous compounding formula, so we have P equals P naught E to the RT, how much would be left in the bank after? And then we have different periods, different amounts of years. So we're going to calculate. So in 1 year, we're going to have $1. Well, let's kind of break this down. So P naught is $1. And then we have E to the 0.05, because that's the interest rate, times time. And then we're going to plug in for different amounts of time, which means you can actually set this up. Whoops. And if we type in for y1, e to the 0.05 x. And if I go to my table, let me make sure it's set up to ask and auto. And I'm going to delete things I have in there already. And now I can just type in a 1, and I see that it would be $1.05. Type in a 10, and you would have $1.65 if you round it to the nearest cent. Type in a 50. So I'm just changing the years because I've put it in as a formula. And you would have $12.18. So not a whole lot of money. Type in 100, and we would have $148.41. Of course, you're probably not alive anymore at that point. Type in 200, and you would have, all of a sudden, we see this jump, and I need to go up here to see what that value is. So we have $22,026.47. And if we type in 500, whoops. Okay, my calculator has froze. Okay, back in business. So notice this number, this huge number, and this is actually over $72 billion. And you can read what it says on the paper if you want to. I'm going to leave that for you to read that. Okay, so our next problem says that you plan to invest $10,000 in a CD, which is a certificate of deposit, for 5 years. There are 4 CDs available to you with the following rates and compounding. Which one gives you the best deal? Show your work. So if we are to, we're going to use the compounding formula. So for this first one, we're going to have, let's remember what this is. P equals P naught. We've got 1 plus R over N to the NT for these first 3. So for this first one, N is just 1. So we're going to have P naught. So we're going to have 10,000. And then we're going to have 1 plus 0.0315. So 1.0315 to the, for 5 years. And so N is 1. So we just have to the 5th power. If you work this out, I already kind of pre-did them, you get $11,677.40. Compounded quarterly, remember N equals 4. So when you substitute this in, you're going to get 10,000. And here you'll have 1 plus your rate, 0.0315, over, I'm sorry, 0.031. There's no 5 on that one. They changed it. Over 4. And then 4 times 5, because it's 5 years, but remember it's NT, so you're going to have a 20. If you work this out, you will get $11,669 or $11,669.60. Monthly, N is 12, so we're still using the same formula. So we're going to have 10,000, 1 plus 0.0305 over 12. And we're going to have 12 times 5, which is 60. If you plug this into your calculator, you will get $11,645.17. And for this last one, it's the continuous formula. So now we have P equals P naught e to the RT. So we're going to get 10,000 times e to the 0.0303 times 5, because that was t. If you evaluate this, you will get approximately $11,635.78. So now we're comparing. Notice they changed the percentage rates on these, changed the compounding. Which one gives you the best deal? It's the one that gives you the most money. And it appears that this one would give you the most money. At the birth of their child, Mr. and Mrs. DeGeneres wished to give him a new car worth $20,000 upon his graduation from high school when he is 18 years old. That would be nice. How much should they invest at 3.25% APR, compounded quarterly, in order to have the money available to this boy, how about his son, or their son, upon graduation? How about if they can find a bank that gives the same interest compounded continuously? So a couple different options that we have to figure out. So first of all, notice that this is now not P. We're solving for P naught. So this is P. This is how much money they want to have. We're trying to solve for P naught. So when we plug it into that formula, this goes in for P. We don't know P naught. We're trying to find that out. We have 1 plus, the interest rate is 0.0325. It's being compounded quarterly, so that means N is 4. And it's going to be for 18 years, so we have to do 18 times 4. So this is what we're going to have to work out. So you can actually do this on your calculator, and notice I can even just type in 18 times 4 there. So when I do that, I get this for my answer. That's this part. But now to work this out, I need to do 20,000 divided by that to solve for P naught. So I'm just going to take on my calculator 20,000 divided by the previous answer I just got. I can recall that if I do second and then hit this key for that's going to take that previous answer. And so now I get P naught is $11,168.49. So that's how much they should invest. Now notice that this means that they're just putting it into the account and leaving it for 18 years. And they're not touching it. They're not putting anything else into it. That's assuming that you can lock in this interest rate and have it for the entire time. So that would be the one way. Then second was, what if you found a bank that did it compounded continuously? So now this is still the part that we're trying to find. We want to know what P naught is. And we have E to the RT, so 0.0325 times 18. So again, remember this is just a number. So I'm taking 20,000 and dividing by whatever this is equal to. So you can even do this in one step. 20,000 divided by, and then I'm going to put parentheses here. I probably wouldn't have needed it. E to the 0.0325 times 18. And I get that P naught is approximately $11,142.12. So notice the compounded continuously, because you're going to make a little bit more interest than you are compounded quarterly, which is why you don't have to start with quite as much money, so that's how come it's less. So on this next problem, George W. wants to double his money in 10 years. Find the rate of interest he would need if his money compounds continuously. So we're using this formula. So they don't tell you how much money he starts with. In the past, we've kind of had some problems where you knew that. So we don't know that. We just know he starts with P naught amount of money. Well, think about how much if he doubles his money, if he starts with P naught, then that means he has to end with twice P naught. So I can think of it like this. Actually, I could fill in some values, huh? So we have 10 years, but we don't know the rate. That's what we're trying to solve for. So notice that I have a P naught on both sides. I can divide both sides by P naught, and they're going to cancel out. So I end up with 2 equals E to the 10R, and I am trying to solve for R. Well, this is an exponential equation. So how do I solve exponential equations? I have to use logs. Since this is an E, I'm going to use natural log, so I'm going to natural log both sides. So I get ln2 equals, this is going to cancel out and leave 10R. So now I know that R equals ln2 divided by 10. So if we take ln2 over 10, we get R is approximately 0.069, which would be about 6.9% would be the rate. So then we're asked, well, what if he wants to triple his money and he's okay with taking 20 years because he wants to triple his money. So this time, if we are starting with P0 and we want 20 years instead, if we triple our money, then we have 3 times what we started with, and the P0s are going to cancel. So hopefully you can kind of see that pattern there. So if you natural log both sides, so we end up with ln3 equals 20R, and that means that R equals ln3 over 20. So if we take ln3 divided by 20, we get that R is about 0.055, so we get about 5.5%. Now I want you to notice this pattern. When we were doubling our money to get the rate, it was ln2 over 10 because it was 10 years. Tripling our money, we ended up with ln3 over 20. So there's kind of a pattern there that we're going to use on the next problem. So the next problem talks about something called the rule of 72. And this is something that is common in the financial world. The rule of 72 states that the length of time it takes an investment to double can be approximated, so we're just approximating in this case, by dividing 72 by the APR. And so instead of an 8, for the 8%, it's just 8. You don't say 0.08 for the using the rule of 72. So it says compare the actual length of time it takes for money to double compared to the rule of 72 for different interest rates compounding continuously by completing the table. So the rule of 72 part is going to be easy because we're just going to take 72, you're going to take divide 72 by the APR. So like here, I would take 72 divided by 2, which obviously I wouldn't need a calculator for, and we get 36. So this would say it would take about 36 years approximately if you wanted to double your money. And if you had a APR of 2%. So if you had 3%, you would take 72 divided by 3, and it would take you approximately 24 years. And here we're going to take 72 divided by 5, so it would take approximately 14.4 years. 72 divided by 7 is about 10.3 years, and 72 divided by 10, which of course is 7.2. Okay, so how does that compare to the actual amount of time using the formula for doubling your money? Well, remember, if we were doubling our money, then that means whatever we start with, so it's kind of, this is our starting basis. So these are going to cancel. So you're always going to end up with this if you're doubling your money. So if I natural log both sides, then I'm always going to end up with ln2 equals r times t. So then if this time I'm trying to solve for t. So t is just going to be ln2 divided by r. But this time r is a decimal value. So if you take ln2 and divide by 0.02, this is going to be what it actually would be, not the estimate. You get 34.7 approximately if you go to the nearest tenth. So I went ahead and typed this in to Y1 and then made sure I was set up to ask an auto and then filled in these values and filled in my chart. So then you can kind of see they're not exact, so that rule of 72 is an estimate. Of course, once you know this formula, it's pretty easy to find the doubling time for any rate. So here you have a nice formula for that. So if you take the time to read over this page, it really addresses the fact that you have two formulas. So we have two different ones. One we talked about, and both of these deal with exponential growth and decay. So the one that we specifically used for financial growth is because we're compounding. And it goes through an explanation about how the formulas really are derived from the same idea. It really does come from the same thing. But it does get confusing if you are, having a dividing by a fraction. So it really is easier to just kind of keep track of the two different formulas. And if you're compounding, then you're going to use this compounding formula. So this next problem is kind of interesting in that it's not financial, but it talks about compounding. So because it talks about compounding annually, quarterly, and daily, then you would want to use that particular formula if you were doing that problem. So for this one, you would actually use P equals P naught 1 minus R over N to the NT power. So we're going to use this formula. So then filling in what we know, we have 500 grams of a substance that we're starting with, and it's decaying exponentially, but then because they ask us to do annually, quarterly, and daily, we're going to use this formula. So we would have R is 0.019. We're going to be putting that over N, and then we have an N here. So for part A, we're going to let N equal 1. For part B, we're going to let N equal 4. For part C, we're going to let N equal 365. I'm going to pause this so I can put this into my calculator since I only have one variable, and then that's just going to be easier to plug that in. So here it is in my calculator, and when I go to my table, I see that I get these values. So we have 490.5, and this would be grams. That's how much is going to be how much is left. So this is always telling me the part that is remaining. If I needed to know how much had decayed, then I would have to do 500 minus that. So you got to watch out for what kind of question it is. For this next one, it would be 490.57 grams. Oh, yeah, that's okay. And for this last one, 490.59 grams if I went to the hundreds place. Okay, so that's what you could do that to figure those questions out. And on this last question, first of all, it should have been in problem 17 instead of 14. So in problem 17, suppose the rate of decay, oops, didn't want to do that. Suppose the rate of decay is 1.9% continuously. Determine how much of the substances is left in a year. Now, we have not talked about this equation in terms of decay. We've only talked about this equation in terms of growth. So if you just looked at this without really thinking about it and you just said, okay, well, okay, I thought it was going to freeze again. If you just took this and said, well, I'm just going to plug these values in and say, what was the amount again? 500 is what we started with, 500 grams times E to the 0.019, and it was in 1 year, so T would be 1. If you just did this, 500 times E to the 0.019. So say you just thought, oh, I'm just going to use that formula. All of a sudden you get this larger value, but this is supposed to be decay, not growth. So what you have to think about here, this has to be a negative. So when you, and we're going to be dealing with that later, where that value, if it's a decay, that constant right here is going to be negative. So now if you evaluate this, 500 times E to the negative 0.019, you get about 490.59 grams, which makes more sense for our other problem that we did as well, and for the last problem. And we're going to see more of that when we talk about some more decay problems. So that's, sorry it took so long, but that should take you through all of the homework problems that you need to do, and you need to have that homework assignment done by the next class time.